All right, guys, thanks for joining me. You can see, obviously today's lesson is about what's called covalent bonding. The previous lesson we learned about ionic bonding. This is a different way in which atoms can interact with each other. He says, I think I can truly say that in this book we have all the elements of a first-class thriller. Analytical chemists as book reviewers. There's a book reviewer, they review the book and the plot and all that, but he's an analytical chemist. He's actually breaking down the chemical composition of the book itself. See, it's primarily carbon. It says Bill's denial at the end of summer was getting serious. He's determined to prolong summer. You guys like that? Well, our summer was gone a long time ago, right? Covalent bonding. Ionic bonding, a little review, guys. You guys remember what the prerequisite was? Remember, you had to have one element with high electronegativity, that would be on the right side, upper right in particular, and then another atom with low ionization energy, that would be on the left side of the periodic table. So basically you needed a nonmetal and a metal, right? Because the nonmetal strongly attracts electrons, the metal gives up electrons relatively easily, and so then you would actually have a transfer of electrons from the metal to the nonmetal. So here's essentially the ionic bond, guys. Write this down. An ionic bond involves the transfer. Notice that's the key word. It's electrons are actually transferred from the metal to the nonmetal. And you guys remember when the metal gives up electrons, it becomes positive. When the nonmetal gains electrons, it becomes negative. And what holds those atoms together is that electrostatic attraction. Remember, opposite charges attract. The oppositely charged ions have an attraction for each other. That holds them together. That's called an ionic bond. Here's a question. You guys, it's a question, so you don't have to really write it down. What if both atoms have high electronegativity and neither can pull an electron away from the other? Right? You guys think both have high electronegativity. What are we talking about? On the right side of the periodic table, right? We're talking about nonmetals. What if you had two nonmetals? Well, what's going to happen is, since neither is going to pull the electrons away from the other because they both have a strong attraction for electrons, atoms of this kind will overlap their orbitals. So you just imagine electrons are orbiting each respective nucleus, but they're going to overlap those orbitals, and so then the electrons would then orbit both nuclei. And what would they do? They would share pairs of electrons. Share, Miss Carrie. And that would form what we call, what do you guys think? What was the title of today's lesson? Covalent bond. And you guys think about it, even the word itself should make sense. You think about think about words that you have with co in it, co-worker, co-ed. Doesn't co mean together? And what's coming together? Valence. Which electrons are we talking about? The valence electrons, always the electrons in the outer shell. So it's when outer shell electrons are shared between atoms. Okay, so notice this. This is the definition. Covalent bonds involve the sharing. Remember, ionic bond was a transfer between metal and nonmetal. Covalent bond is the sharing of electrons between two atoms with high electronegativity. And we're saying atoms with high electronegativity? What kind of atoms are we talking about again, guys? That's right. We're talking about nonmetals on the right side of the periodic table. I'm kind of going like if our periodic table's right here, the right side of that periodic table.
Each single hydrogen atom has an electron configuration of 1s1.
So you guys, when I say the right side, you guys remember the one exception is hydrogen. You guys, hydrogen, I don't know if you guys can see this periodic table. Remember, we tend to put hydrogen here, but really hydrogen, even though it's on the left side, we should know hydrogen is not a metal, it's a non-metal. So that would, we would expect two hydrogen atoms, if they were to interact, to form a covalent bond. And here's why. So check it out, guys. Think about it. If I did the Lewis dot structure, right? Hydrogen has one valence electron. It only has one electron, right? And I'd ask you, is hydrogen happy, fat, content, stable by itself? No. You guys, when do we say atoms are happy, fat, content, stable? When their outer shell is full. Imagine another hydrogen atom. That has one electron. Is that happy by itself? No. Remind you guys with the periodic table, how many total electrons would be required to fill hydrogen's outer shell? Well, you guys look. If you just go across, remember all you have to do is just count across a period. There's 1, 2. Remember there's a maximum of 2 electrons on that first energy level. It's still 1s2. So how can hydrogen achieve that noble gas electron configuration where its outer shell is full? If these electrons are shared. They share a pair of electrons. So rather than just one electron orbiting its own nucleus and another electron orbiting its nucleus, they share it. And so these electrons orbit both nuclei. And that's what it's showing here, right? This is the electron cloud, the orbital, right? Remember, it's a spherical, it's s orbital. So what they do is they overlap. And so now those electrons are orbiting both nuclei. And so hydrogen always exists as a diatomic molecule, H2.
Therefore, covalent bonding involves the sharing of electrons between atoms, as well as an attraction force between the nuclei of atoms and the shared electron.
Hold on, guys, 1 second. So you guys, there is a faint amount of pure hydrogen in the air, a small amount, like maybe 5%, 0.1% of all the air might be hydrogen, but it doesn't exist as a single individual atoms. It exists as a diatomic molecule, and you guys see why, because by sharing that pair of electrons, now both hydrogen atoms are happy, fat, content, stable, and this is how hydrogen would be found in the atmosphere. Okay, so the question is, between what kind of atoms could an ionic bond form? So this is a question I'm hoping you guys would just pause it and think, okay, between what kind of atoms? We're kind of doing a little review. When it's an ionic bond, hopefully you guys guessed correctly, between a metal and a non-metal. Remember, opposite sides of the periodic table. Between what kind of atoms would we expect a covalent bond to form between? Remember, ionic bond is when electrons are transferred. Covalent bond is when electrons are shared. Between what kind of atoms, guys? You should have guessed it. Two non-metals. Okay, guys, this is a very important concept we're going to bring up, so make sure you guys are writing this down. If the shared electrons are not shared evenly, so you can have a sharing of electrons, but maybe in a situation the electrons are not shared evenly because one of those atoms pulls on the electrons harder, and thus the bond has what we would have like positive and negative ends. When you guys agree, the side where the electrons are spending more of their time would be the negative end, and the side where they're spending less of their time would be the positive end. We'd say that they have poles. We'd say the covalent bond is polar. You guys, this is an important concept. Make sure you write it down. If the electrons are not shared evenly, we'd say the covalent bond is polar. When you guys think about this, think about when you think of polar, you're probably thinking maybe like North Pole, South Pole. You guys know the Earth is one gigantic weak magnet, right? And then you guys know on a magnet you have a North Pole and a South Pole, which are the opposite poles. Just like in electric charge, you have positive and negative that attract. And so unlike poles of magnets attract, right? But anyways, the reason why the Earth is a gigantic magnet because it has a North Pole and a South Pole. There's not there's ends of a magnetic field, two ends of a magnetic field. So hopefully that'll help remind you guys when we use that word polar, we're saying that it has positive and negative ends. Okay, we're gonna talk a little bit more about this. So you guys think about it, if you had two atoms and one's pulling on the electrons harder, which one's gonna pull on the electrons harder? The atom with, you guys remember from our previous lesson, a couple previous lessons ago, the one with higher what? The more what atom? You guys remember that term? The more electronegative one. You guys remember electronegativity is a measure of the tendency to attract electrons. So if you had an atom that has a higher electronegativity than another atom, and let's say they end up sharing electrons, but the one that's more electronegative is going to pull the electrons closer to itself, those electrons are going to orbit its nucleus more often than they would the other atom. We would say that even though we'd say because the electrons are being shared, it's a covalent bond, but because they're being shared unevenly, it's a polar covalent bond. So look at an example of this.
Electrons are attracted more toward the larger chlorine nucleus than to the hydrogen nucleus.
Okay, so once again, two nonmetals. So if they were going to interact, you might expect them to share electrons, and you guys see what's happening is they're kind of overlapping their orbitals. This is kind of representing the space where you would find the electrons, right? They're orbiting. So therefore, it would look like this. So once again, we could do the electron dot structure for hydrogen. Once again, hydrogen just has one electron. Is hydrogen happy, fat, content, stable on its own? No. Remember we said it would need a requirement of two, you guys remember hydrogen here, first energy level, two electrons to fill its outer shell. Then think about chlorine. Chlorine, you guys remember which electrons are we interested in? only the valence electrons. So if chlorine's right here, okay, all I do is just count over. It's got 1, 2, guys look, first of all, look, chlorine has 3 shells of electrons, 1, 2, 3. The first 2 shells are full, and so the outer shell, that third shell, contain what we call the valence electrons, right? Those are the ones we're concerned about. 1, 2, 3, 4, 5, 6, 7. It's got 7. So I would put 7 dots. So now just look at a chlorine atom by itself. Is that going to be happy, fat, content, stable, existing monotomically? Mono meaning as a single. Hopefully you guys would agree it would not. In fact, how many total electrons are required to fill chlorine's outer shell? If you count across to the noble gas, remember the noble gas have filled outer shells, it's 8. So what would you guys predict would happen? When you guys predict that they would share these electrons. So these, the valence electron from hydrogen and one of the valence electrons from chlorine would orbit both the hydrogen, and that's what this is showing here by the overlap. Those electrons would orbit both nuclei. And that's what holds the atoms together, because those electrons are orbiting both of those positive nuclei. Okay, now the difference is, so these are being shared. The question is, are those electrons being shared evenly or unevenly? Well, hopefully you guys would realize they're being shared unevenly. And the question is, which nucleus, the hydrogen nucleus or the chlorine nucleus, is going to have a stronger attraction for those electrons? And hopefully you guys would guess correctly from the previous 2 lessons ago about electronegativity. Where are the most electronegative atoms? You guys remember? Where in the periodic table? It's the top right. Obviously, with the exception of the noble gases, top right. And so I look on my periodic table and I see chlorine is over here, hydrogen's over here, chlorine's closer to the top right. Therefore, it must, I would predict it has a higher electronegativity. So these electrons are going to spend more time around chlorine. So if that's the case, here's what we show, guys. So these electrons are going to spend more time on this side of the, so what I would do is I would point an arrow to the side where the electrons are spending more of their time. You notice how I make the arrow. I kind of put this on this side. So this side is what we call partially negative. Now you guys, this is a Greek letter delta. In this case, it means partially. So this side of the bond is partially negative. And this side, look at what the arrow looks like. Doesn't it look like a positive sign? That kind of reminds you, oh, this side would be partially positive. Hopefully you guys understand what we're saying. Notice why it's partial. Remember, it's not really a full charge because electrons aren't necessarily transferred from one atom to another like an ionic bond. Remember, in an ionic bond, electrons are transferred from the metal to the non-metal, so then the metal has less electrons and therefore becomes positive, and the non-metal has more electrons and then it becomes negative. But notice the electrons are still being shared, so we don't say a full charge, we just say a partial charge. That's what this indicates, partially negative, partially positive. We would say that this here is a is a polar covalent bond. It's polar. Why? Because it's got positive and negative ends, because the electrons are shared unevenly. Okay.
The molecule has an end with a partial positive charge, the hydrogen end, and an end with a partial negative charge, the chlorine end.
Okay, and then compare that with hydrogen here, H2.
I remember that hydrogen is a diatomic element. A molecule of hydrogen gas has 2 atoms of hydrogen.
You guys see what this is? You guys would know it as a blimp. You guys know who originally created the blimp? It was the Germans, and they called it a Zeppelin. You guys remember the first one? You guys ever hear about that history? Notice it's like black and white. This was, I think, a picture of the Hindenburg. And you guys, why would they fill it with hydrogen? Well, you guys should know hydrogen's really light, and so therefore it's gonna float because it's less dense than the air around it, right? But we don't fill blimps now with hydrogen anymore. Does anyone know why? Tell me. Okay, you can't tell me. Hydrogen gas is flammable. And you guys might know that history. There was a spark. Yeah, this was in the 40s, 30s. I don't know the exact history. But they actually had a spark, and the thing just came down in flames. In fact, guys, that's where that heavy metal band, I don't know if the heavy metal, but like a hard rock band, you guys heard Led Zeppelin? You know, they got their name from the Zeppelin. Remember, this is called the Zeppelin, and when it caught fire, it kind of fell from the sky like lead from the sky, so they got their name Led Zeppelin from that. But anyways, So look at hydrogen here. Once again, this is a covalent bond because electrons are being shared. This is a covalent bond because electrons are being shared. But this, however, is a polar covalent. But then you look at this, you guys think about it. Would you guys expect either of those hydrogen atoms to pull on the electrons more strongly than the other? No. Therefore, this does not have positive and negative ends. Just think about it. These electrons are shared evenly between those two atoms. We would say that this covalent bond is what we call nonpolar. You guys see why it's called nonpolar? Because it doesn't have ends. It doesn't have positive and negative ends. Remember, polar, think North Pole, South Pole, like on the ends of the Earth. Therefore, it's called nonpolar. A lot of students I found in times past, they always get these terms confused. Nonpolar means no ends, polar means positive and negative ends. So put this, if the bond is nonpolar, that's when the shared electrons are shared evenly. The bond does not have positive and negative sides. There are no poles. That's why we say there's no nonpolar. No poles. All right, guys, almost done. Hopefully you guys are following this. You guys, it's really important, covalent bond. So the major things today are being able to recognize a covalent bond and then being able to recognize, is it a polar covalent bond or a non-polar covalent bond? So sitting at the restaurant, I guess I'll try the veggie burger. Do you want anything else, anything with that? What do you recommend? He says, well, how about a beef salad? Right, to kind of offset that veggie burger. Okay. All right. Little review, guys. What kind of bond results between two atoms with extreme differences in electronegativity? So if you had two atoms and there was a big difference in electronegativity, one had extremely large electronegativity, one had a very small electronegativity, what kind of bond hopefully you guys can get? Yeah, we're going back to a previous lesson. That would be ionic. Like metals have very low electronegativities. Remember, they tend to give up electrons, not attract electrons. And then nonmetals have relatively high ones. What kind of bond results between two atoms with relatively high electronegativities? Two atoms and they both have high electronegativities? You guessed it, not an ionic bond, but a covalent bond. Okay, so, you know what? Let me just show you guys here. Here. I'm going to show you guys a table of electronegativity values. Or actually, it's the periodic table. And you guys will notice, check it out. You guys will notice, look, for the most part, look, a lot of the noble gases, they don't even have this is electronegativity values, they don't even have it. And then there's some other ones, don't worry about that. But for the most part, remember, noble gases don't have an attraction for electrons. But as expected, you guys, where will we expect to find the most electronegative atoms? Upper right. And if we look, fluorine indeed has the highest electronegativity value. You guys look, oxygen's pretty close at 3.5, chlorine's 3.0. And then now you guys look at the metals. You guys see 1.0, 1.5, 0. They have very low electronegativity values, meaning they have a very low attraction for extra electrons, okay? So that being said, what if we had a situation, so what we do is we compare the electronegativity values of the two atoms in question. What type of covalent bond results when there's a significant difference in electronegativity? So let's say the difference in the electronegativity values is pretty large. So we compare one electronegativity with another. What type of covalent bond do you guys think that would be? What do you guys think? Wouldn't that be a polar covalent? Because if there's a large enough electronegativity difference, won't one of them be pulling on the electron more strongly than the other? And therefore you're going to have positive and negative ends. What type of covalent bond results when two atoms have very similar electronegativities, such that the difference is just a very small value? Just, they're pretty similar in electronegativities. What kind of covalent bond do you guys think you get? Hopefully you guys guessed it. A nonpolar, because in that case, the electrons would be shared relatively evenly. So, you guys are going to put together a flow chart to kind of finalize here. At the very top, what do you guys think would go over our last 2 or 3 lessons? What do you guys think would go at the very top? What have we been talking about in general? Overall kind of unit. Hopefully you guys get it. The first would be bonds, or bonding. We're talking about bonds. And then you guys see 2 arrows come off of that. What kind of bonds do we have? 2 big categories of bonds, ionic and covalent. And now look at that covalent. We've got 2 coming off of covalent. Covalent bond could be either what or what, guys? Polar or nonpolar. So now how do we tell the difference between ionic, polar, and nonpolar? We look at the electronegativity differences between the 2 atoms. And here's what we have. So if you look at the electronegativity difference, you guys know arrow pointing to the right means greater than. So if the difference between the two atoms, electronegativity, is greater than like 1.7, we would identify that bond as an ionic bond. If the electronegativity difference between the two atoms is kind of like in the middle, kind of between 0.5 and 1.7, we would identify that as a polar covalent bond. And if the electronegativity difference between the two atoms is very small, essentially they're very similar electronegativities, how we would identify the bond between them is non-polar covalent. So, you guys, we're going to, I'm going to finish with just like a little, I want you guys to try to figure it out, okay? So the first thing I have is, what type of bond would you predict to form between boron and sulfur? Okay, so let's look at this, boron and sulfur. So hopefully you guys have this written down, and as we do this, you're looking at this and you're looking at the periodic table I'm going to show you here with electronegativities. So between boron and sulfur, what kind of electronegativity, or I'm sorry, what kind of bond would you identify as occurring between boron and sulfur? Okay, boron here, sulfur here. Kind of bond, what do you guys think? Now you guys look. First of all, boron has an electronegativity value of 2.0 and sulfur has a 2.5. But you guys, even right off the bat, you know what you can say right off the bat? You should know it's a covalent bond. Why would you predict a covalent bond? Because these are both non-metals, so you're thinking covalent. Then we look at the electronegativity difference. I go, this sulfur is 2.5, boron is 2.0. The difference, you just subtract it, is 0.5. Looking at your chart, is that a extreme difference, significant difference, or minimal difference? And if you look at it, it is a significant difference such that you would conclude that a polar covalent bond would form between. So boron and sulfur will share electrons, but the electrons are going to spend a lot more of their time around sulfur, creating positive and negative ends like hydrogen and chlorine. Okay, another one. What type of bond do you think would form between calcium and nitrogen? Calcium and nitrogen. So look at the periodic table. I'm hoping you guys pause it here so you guys actually have time. I'm hoping you guys can actually see the values. Calcium and nitrogen. I'll show you guys. Calcium is here and nitrogen is here. So if a bond formed between them, what type, how would you identify that bond? Okay, right off the bat, you guys, you should be able to identify it as an ionic bond, simply because calcium's a metal, nitrogen's a non-metal. You think, oh, it's probably going to be ionic. Nitrogen is actually going to take electrons from calcium, and you guys see why? Because nitrogen has such a high, its electronegativity is so much higher than calcium that it'll essentially pull electrons, valence electrons from calcium. In fact, if we looked at the electronegativity difference, 3.0, calcium is 1.0, the difference is 2.0, and if you look on that little that flow chart that we just wrote, that corresponds to an extreme electronegativity difference, indicating an ionic bond would occur. Last one, you guys, what about between carbon and hydrogen? Between carbon and hydrogen, you guys, this is a key bond because you guys, this occurs in a lot of organic molecules. Organic meaning from living substances have a lot of carbon-hydrogen bonds, so that's why I bring this one up. So what type? How would you identify the bond between carbon and hydrogen? Hopefully you guys are thinking, okay, carbon is right here. Hydrogen, even though it's on the left, you guys got to remember hydrogen is still a non-metal. Okay, that's kind of, you know, some people think it's kind of strange that they put it on this side, but that's all right. Sometimes actually, periodic table, sometimes people put hydrogen right in the middle, but you guys are thinking two non-metals, so you should be thinking covalent. Then you're thinking, okay, non-polar, polar, so you look at the electronegativity difference. Carbon's 2.5, hydrogen 2.1. The difference is 0.4. And based on what we had written down, that's only a slight difference in electronegativity, and therefore they're going to share electrons pretty evenly. Therefore, we concluded. So, what kind of covalent bond? A non-polar covalent bond. All right, guys. Thanks for joining me. We'll see you next time. Bye.